Okay, let's get started. Welcome to Module 3 for 16A. You've made it this far. There's only the last third of the class to go, and it's a short third. So if you've been holding your breaths, the end is almost here. You're almost going to get to go, and Thanksgiving break is along the way. So we will be entering this last module, and Module 3 is a module that is nominally called the machine learning module, and it's really building heavily on everything that we've been working on in Modules 1 and Modules 2 up until this point. So Module 1 really talked about an introduction to systems, right? And thinking about how can we take a real-world problem and model it to make it into a mathematical form so that then we can, try to understand it. And so you saw problems on the homework that were of this type, right? For example, the Segway problem is one example. There were problems about trying to understand the flight of quadcopters, right? And trying to use vectors to model basically the spaces that quadcopters can actually travel in. And then there were the other kind of highlight of Module 1 was to try and really understand the PageRank algorithm, right? How can we use a very simple model about how people move from web page to web page by clicking based on the number of links between the pages to therefore understand a notion of steady state probabilities. When people have clicked on all of these pages and at steady state, which pages are more popular than others. This was kind of everything you saw in Module 1. Module 2, then, you said, well, we've been doing all of this modeling, but what use is it if we only have models in our head and don't actually do anything in the physical real world, right? And here you delved very deep into understanding how models for specific physical components, such as resistors and capacitors, and finally the coolest part, which is op-amps, can actually have you, build things and design, interesting things that can actually do things that you want in the real world. And so the last lecture was talking about how to design a LiDAR sensor, right? And your entire lab module was working around how to design basically a touchscreen. So you talked about two different kinds of design, where you talked first about the resistive touchscreen and then also about a capacitive touchscreen. And just to think about what you did there, right? First, you said, well, let's understand simple models for these physical components. And then, through this process of design, to some extent trial and error, but also a lot of systematic thinking, you are able to think about how we can put them together to build, say, a touchscreen or a LiDAR sensor. And you saw this iterative process, right? You suggest something, you try something, and you're like, oh, well, maybe this isn't quite working. How do I tweak it a little bit to try and then improve, right? Well, Module 3 is trying to take both of these ideas together. And really, you can think of all of Module 3 as one big, giant design problem. This module is structured in a way that throughout the module, every single lecture, we will build up one small part of how we can build a GPS localization system. How many people have used a GPS system before? Pretty much everyone, right? And what we're going to do is we're going to basically break down this very complex problem of designing a GPS system into small parts. We are going to model them, and we're going to take the step further of actually seeing how we can design algorithms that will do what we want our systems to actually do. And in the process of designing this GPS system, you will be exposed to a lot of the fundamental problems that show up in machine learning. So you will get a sense of what are the core ideas in this field, and what are the tools that are used to build these things out. So, for a lot of you, you might have heard this word machine learning before. How many people have heard the word machine learning? How many people feel like, oh, maybe it's not really clear what machine learning exactly means. Right? How many people have heard terminology talked about, but it's not clear what machine is learning what? Are you actually processing some kind of data science? These are all different terms, and really machine learning it's a little bit of an ambiguous and large group of things, and there are algorithms and ideas that are talking about how can we take information from the real world and organize it and represent it so that then we can use this information to, extract generalizable principles about the real world. Of course, this is one very big phrase, right? And so machine learning is often broken up into problems such as classification. What is classification? Classification is, I see an image on the internet and I want to predict whether this image is a cat or a dog, or I want to classify this image as a cat or a dog. I get in a bunch of pixels and I want to now generate a label. This is kind of a canonical classification problem in machine learning. That's one type of problem. Another type of problem in machine learning is an estimation problem. You want to be able to estimate some kind of parameter from data. A third type of problem is a prediction problem. So, for example, you want to look at historical data on the stock market and predict how it is going to behave, right? That would be a prediction problem that, machine learning traditionally thinks about quite often. Or you're driving an autonomous vehicle and you see a pedestrian who's walking along, and you want to be able to predict the path that pedestrian is going to take because your car had better not, drive into this pedestrian. So these are the kinds of problems that, for example, a prediction algorithm in machine learning might want to do. Another algorithm another idea that is quite useful and, often comes up in machine learning is a clustering problem. Where you have a bunch of data points, or you have a bunch of examples or instances, and you want to somehow cluster them into instances that are similar to each other. This is related to the classification problem, and also often lots of clustering algorithms are used for classification. In fact, you'll see in 16B a lot of more detail in clustering problems. So in 16A, in this module, for this semester, we're going to try and talk about the first 3 machine learning problems. And if we have time, we might talk about a little bit more ideas, but we'll see how the course goes on. These are what are called machine learning problems. But there's also what we want to talk about is we don't just want to talk about problems, but we also want to talk about techniques that can be used to solve these problems, right? Just talking about problems isn't particularly interesting. So, what are the techniques that we are going to use to solve these? And here we're going to be really heavily building on what we did in Module 1, where often one of the most effective ways to make progress in a very unknown field is to try and build models. Take your data and try and represent it in some kind of structured way. Make a model. It might not be the best model, it might be a crude model, but make a model and use that to understand. And so we will be doing a lot of making of models. And a second tool that we will use quite frequently is optimization. And optimization will come in conjunction with the modeling, where what we will be trying to do is we will be trying to optimize an error metric. So when you think about this problem, right, you see a bunch of pixels and you want an algorithm to predict whether these pixels represent a cat or a dog. Right? When you're talking to a human, when you're talking to your friend, you can define, you can discuss, well, I'm looking at this picture, is this a cat or is it a dog? As a human, we have an intuitive sense of whether the animal in front of us is a cat or a dog, right? But now when you want to have an algorithm predict whether something is a cat or a dog, how do you communicate to that algorithm this intuitive sense of catness or dogness? Right? Does everyone see that there's maybe some kind of challenge here? Like, this is a very human notion. And somehow we want to have this human notion translate to a prediction that a machine can then make. And so for this, what we end up doing is we often try and define a structure for the problem and define an error metric. And you say that, these are certain properties that a cat should have, these are certain properties that a dog should have. You extract what are called feature vectors and use this to help define these kinds of notions of correctness. Of course, as you can imagine, there's probably many different ways to define what types of pixel arrangements should make up a cat and what types of pixel arrangements should make up a dog, right? And this is what leads to all of this research in machine learning, where you're actually trying to understand, well, what kind of modeling should I do? What kind of assumption should I make? What kind of algorithm should I then run? We're not going to be able to get to all of this in the next 3 weeks of class, but this is what awaits you on this further trajectory. What we are going to get into is the basic modeling techniques and how an engineer or a computer scientist can start thinking about these problems. So today, we are going to actually tackle this problem of defining an error metric and trying to build out from there. So the problem for today's problem is classification. And we're going to be thinking about classification in the context of the GPS problem. So we will talk about an intro to the GPS problem. We will define what inner product means to help us do this. We will talk about the Cauchy-Schwarz inequality. And finally get to our satellite classification problem. Okay, any questions thus far? Great. So before we go forward, I just wanted to bring up a point of feedback that I had received. And I heard from some students that sometimes they want to be able to sit with students who also want to have small discussions about the course material during a lecture. And I know that sometimes, in such a big class, you don't always know too many other people who are in lecture. So if you are in lecture and you feel like you would want to sit with, you don't always have a consistent person or a set of people that you can always sit with. If you want to find such people to sit with in lecture, please hang back for a couple of minutes at the end of lecture, and we'll try and make small groups of people who can sit together. Okay, small announcement. But now with that, let's get into our design problem. Which is a GPS system. What does GPS stand for? Global Positioning System, right? Does anyone know how GPS works? Some rough ideas. Yeah? Triangulation is something that's used in GPS. That's absolutely correct. We'll get to talking exactly about what triangulation is in next lecture. Any other things that come to mind? Yeah?
There's about 24 satellites orbiting above. About 8 of them are on the same side as you, which allows data to aim at you at a time.
Yeah, good point. That's what I wanted to bring up. There's 24 satellites in orbit around the Earth. And what is the GPS problem fundamentally? you have these different satellites in orbit around the Earth, and you can think of these as fixed points, right? And what you want to do is somehow, using an algorithm, figure out your position relative to these 24 satellites. And because the 24 satellites are fixed relative to the Earth, you can therefore figure out where you are exactly on the Earth. So if you were to think about this in a simpler setting, for example, if you were to think about this on, a 2D plane or a 1D line, on the Berkeley campus, a good way to define where you are is to say, well, tell me where you are relative to Campanile, right? Or tell me where you are relative to Wheeler Hall or Soda Hall, right? What we do, we always do this, even in our daily interactions, is you use landmarks that are commonly known, and then you use this to resolve ambiguities with someone else to identify their location, right? So you have these 24 satellites, and not all of them are visible to you at any given time. So right now we're inside this room, so effectively none of them are visible to us. But if we were to go outside, you might have line of sight vision to some of them. Otherwise, a lot of the transmissions from these are electromagnetic, so they're not obstructed by visual obstacles, right? So you have some of them that are visible to you. And now, what are the different problems that you want to be able to solve, right? You want to be able to figure out your position relative to the satellites that you can actually see. This is a fairly involved problem. We're not going to be able to solve it in one lecture, not even in two. But before we jump into this module, I want you to, take some time, think on your own. How would you go about solving this problem of finding your position relative to these different satellites? So talk to your neighbor, try and break this down into different sub-problems. Like, think about it as a design problem, right? What are the different sub-parts and sub-small problems that I need to be able to solve to be able to actually, build the app that's on your phone? Okay, so anyone have any ideas or sub-problems that they would want to share with the whole group? What are some sub-problems that we need to be able to solve? Yeah, at the back there. Yeah, you. Great. What was suggested was, well, you have to figure out, or let's say things to figure out, is what is the distance between the satellites and distance between you and the satellite, right? You got to be able to figure this out. What else do we need to be able to figure out? So if I tell you the distance from me and one satellite, someone else. Yeah?
You can figure out how many satellites you need to use to determine your location.
How many satellites do we need to use? Maybe I can put it as how many satellites are enough? Like, do we need to put 1 million satellites in orbit? Why is 24 a good number? Yeah? The location of the satellites. Yep, at the back there. Can we basically the information processing that is required to be able to actually compute these distances? Yep. Yep. Back there. We have to know how to access the data sent from a satellite. Yep. Yep.
We need to sync the time between satellites and the phone.
Great. We need to synchronize the timing. Yep. Try to figure out how, given the distances, how do I figure out what my position is, right? I can just say like, well, I'm, 1 million miles from satellite A, but that doesn't help me generate that blue dot, right? How do I go from these distances to my actual position? Yeah, these are all great ideas. There's one more key challenge that I'm hoping someone is going to come up with that hasn't been brought up yet. The very back? Are all the satellites always moving? Yeah, I guess you need to keep, this is related to keeping track of the location of the satellites. Yeah? Yeah. How to send a signal to the satellite? Yeah, that's a good point, which hasn't come up yet. Signaling to satellites. Yeah, at the back. How to get them up into orbit? Yeah, that's a good problem, but I actually don't know how to solve that one, so we'll skip it. Yeah. How accurate is the data we're measuring? Great. This is the one point that hadn't come up yet. And this is related to the idea of how to deal with noise. Right? When you're getting these signals and you're getting these distances, yes, you're going to compute something, but is it going to be perfect? Right? You're going to get errors in your data, you're going to get errors in your measurements, you're communicating using wireless signals, so stuff is going to break. And what you need to do is you need to be robust to noise measurement, to noise in your measurement. Okay, so these are a lot of problems. We are not going to get to solving all of these this semester. We will not be putting any satellites in orbit. And we will be trying to get to a couple of them. There's another one that didn't really come up in this list, so I'll suggest it myself, which is which satellite am I talking to? Right? If I tell you I'm, 50 meters from either the Campanile or Soda Hall, that's not very useful for you, is it? Right? You want to know what landmark I'm giving as a reference. So, which satellite am I talking to? That's a problem that we will really need to be able to solve. And so, in class in this semester, we're going to be focusing on solving this problem, basically, how do I combine my distances to get actually a position, and dealing with the noise. And in 16B, you will talk a little bit more about the wireless communication parts. So you'll talk a little bit more about the signaling to the satellites. And I guess actually we will also talk about this. And implicitly we will talk about this problem. So of course there's a lot of many different types of engineering that goes into this. And there's a lot of, physics that goes into actually making sure that you can have a satellite and have it be in orbit and have it maintain a constant position. We're not really going to talk about any of that. We're going to assume that there's a bunch of satellites that are in fixed positions and they maintain constant orbit. And we're going to talk a lot more about the signal processing, machine learning, and computation side of things. Are there any questions about this so far? Okay. So today's problem is the classification problem, which is, let's say I'm receiving a signal from a satellite, right? How do I figure out which satellite I'm actually talking to? What kind of signal do I want to be transmitting or sending? What kind of signal do I want to be receiving? What kind of signal should the satellites be transmitting? Right? These are all the kinds of questions that we want to be able to answer today. And for this, I'm going to take a small aside and introduce some kind of a little bit more linear algebra terminology and notation so that we can actually solve this problem going forward. This is something you've already seen before, so you should remember this from Module 1. But I'm going to call it a different name now. I'm going to introduce this idea of inner product. Okay, so let V and W be two vectors. And I'm going to define the inner product of V and W as vector V transpose times W. So let's say V is a vector that is made of the elements V1, V2, all the way up to Vn. W is a vector that is W1, W2, all the way up to Wn. Okay? So vector W is vector W. What is V transpose? It's a row vector, right? These are column vectors. It's a row vector with exactly the same elements. So this I can just write out as V1, V2, all the way up to Vn times W1, W2, all the way up to Wn. And now this is something we've seen before, right? This is just basically a 1 by n matrix times an n by 1 matrix, we can use the exact same rules of matrix multiplication to do this multiplication out, right? What is the dimension of the thing we're going to get out when we do this multiplication? 1 by 1, right? We're going to get out basically a scalar. And what is that going to be? It's going to be V1 W1 plus V2 W2 plus Vn Wn. Or I can write this using sigma notation as I going from 1 to n, Vi Wi. Any questions about this definition? This is called the inner product. Sometimes people might also call it a dot product. Here we're thinking about V and W are always real valued vectors. So their entries are all real valued belonging to Rn. Okay? You will also see that this is very related and is essentially the same as the idea of correlation. So if sometimes someone asks you what is the correlation between two vectors, they're also essentially asking you for the dot product. Yes, question?
So inner product, is there like a notation, like for multiplication you have like X?
Yes, so this, good question, this triangle bracket notation is what we call an inner product. This thing is exactly the notation. What is something that you can notice about this immediately? What would happen is instead of writing V comma W, I wrote W comma V. It's the same, right? So unlike general matrix multiplication, does the order in which you multiply things for the inner product matter? No, this is a special case where actually things are commutative. Okay? What if you take this special inner product of V comma V? What do you get out? You take the inner product of a vector with itself. This is same as sigma Vi squared, right? Is there something else we know how to call this? Is there another name we use for the sum of the squares of the elements? The magnitude of the vector, right? This is basically the magnitude of the vector squared. Also called the norm. Magnitude or norm. N-O-R-M. Okay, so let's do a very straightforward example, right? Let's say V is equal to 1, 1, and W is equal to 1, 1. What is VW? 2, right? What if V is 1, 1 and W is equal to 1 minus 1? Zero. Is V equal to 0? Is W equal to 0? But can you have inner product 0? Yes, right? Different from scalars. Here, what we will see, there's a terminology for this. When the inner product of two vectors is 0, these vectors are called orthogonal to each other. And we will see why that is true. So let us now consider two general two-dimensional vectors. Let's consider V and W. And I want to make a choice about how I'm going to represent these two-dimensional vectors. Right? I can represent a two-dimensional vector as an x-coordinate and a y-coordinate. But what's another way that I can represent a vector in 2 dimensions? You've seen this in Module 1 on your homeworks. Someone else. Yeah. I can't hear you, but you're saying that you don't have to represent it in the basis of, you can use a different basis. Yeah, write it as any linear combination, right? You don't have to write it as a linear combination of 1, 0, and 0, 1. We know that there's many different bases. You can represent it in a different basis. Yep, that's one other great way to represent it. What is a particular way of representing that's rotation friendly? Yeah? Angles. We can represent vectors using angles, right? This way of thinking about vectors is particularly helpful when we want to start thinking about inner products and correlations and so on and so forth. So what's the way of representing a vector that's at a particular angle from the x-axis? If this angle is theta, I can use polar coordinates, right? I can represent this as cosine theta, sine theta, right? If this seems unfamiliar, go remind yourself of the discussion problem on rotation matrices from Module 1. And what is the norm of this vector, cos theta, sine theta? 1, right? So if I wanted to have a vector that was longer than length 1, what should I do? Scale it, right? So I can say maybe alpha times cos theta sine theta. So theta tells me the direction, alpha tells me the length, right? This is a general vector in 2 dimensions. Let's say I can represent W the same way as beta times cosine phi sine phi, right? Okay, so now what is V W, the inner product of V and W? Take a minute and calculate it. V and W are 2 general vectors. Okay, how many people have plugged the numbers into the formula? Yeah? Okay, let's do the plugging in together, right? So I have, what is the first coordinate of V? Alpha cos theta, right? So I basically take V1 W1 plus V2 W2. So I have alpha cos theta times beta cosine phi plus alpha sine theta times beta sine phi, right? So what can I pull out? Alpha beta, and I have cosine theta cosine phi plus sine theta sine phi. Trig identities. What is this equal to? While you're reminding yourself, I'll do some little exercise on the side. What is the norm of V? Alpha. Norm of W. Beta. Anyone's memory remembers what this is? Yeah. This is cosine of theta minus phi. If you don't remember this, go look up your trigonometry textbook. Okay. So, what is alpha? Alpha is now just the norm of V. And what is W? That's just beta. Cosine theta minus phi. Okay? So, let's say this is angle theta here. And this is some angle phi. So this is V and this is W. Okay? So how does this inner product vary as theta and phi vary? Let's say theta is fixed, right? Theta is this fixed angle. And now I have this other phi that's varying, right? If you wanted to maximize the inner product, where do you want this other angle to go? This exactly on top, right? I see people making these hand gestures. Why do you want it to go exactly on top? How is cosine going to vary? What is the largest value cosine can take? When is it attained? 0. So when theta minus phi is 0, that's when this inner product is maximized, right? So inner product between V and W is maximized when theta is equal to phi. How do you make this 0? If you wanted to make the inner product between these two things 0, how would you do that? Regardless of the magnitudes. What does theta minus phi have to be? If theta minus phi is equal to 90 degrees, cosine theta minus phi is equal to 0. Everyone remembers trigonometry, right? Good thing to go remind yourself of. Okay, if theta minus phi is 0, then V and W, their inner product is 0, and the vectors are called orthogonal. That's where the name comes from. Because if the angle between the vectors is 90 degrees, if they're perpendicular or orthogonal to each other, then their inner product is 0. What about everything in between? Basically, by varying this angles, you can basically see that you can have the inner product vary, right? So the inner product is really trying to get at, let's say you fixed the magnitudes of the vectors, right? You didn't change their length. One way, of course, to make the inner product big is to make your vectors really, really big, right? If your norms of your vectors are really big, then your inner product is going to be really big. But the other thing that really matters is the angle between the two vectors. And no matter how big you make your vector, if the two vectors are orthogonal to each other, your inner product is always going to be 0. Everyone with me here? Okay. So this now allows us to state the Cauchy-Schwarz inequality which basically says exactly this. So here I can go one more step, and I can say this. I can always bound this, right? What is cosine bounded by? It's always smaller than 1, right? No matter what I do. So this is always smaller than v times w times 1, right? I can always say that cosine of theta minus phi, no matter what they are, is always less than or equal to 1. So I can use this to write the Cauchy-Schwarz inequality. Which is that the inner product is always less than or equal to the product of the norms of the vectors. And what you've shown here, you've just argued using this derivation that this is true for two-dimensional vectors. Turns out you can actually show that this is true for n-dimensional vectors. You need one small extra tool for that, induction, which you will be learning about in CS70. So those of you who are in CS70 might have already seen proofs of this. We're not going to be asking you to prove this beyond 2 dimensions in this class, because we haven't taught you yet what induction is. But CS70 will talk about this, and you will get to see a full proof of this for any n-length vector. Any questions about this? Basically what this is saying is that if I have 2 vectors and I'm looking at their inner product, I'm bounded basically by the product of the lengths of the 2 vectors. This cosine factor that's showing up can only make my inner product smaller because it's always upper bounded by 1. And this is going to be very important for us as we go forward in our identification problem. So are there any questions about this? Okay, so now that we have some tools and machinery under our belt, let's go back to our original problem, which is that of satellite classification. The satellites are going to be talking, they're going to be sending signals to us. They're going to be sending signals that are basically electromagnetic waves, very similar to the LiDAR example that was talked about last class. And what we want to do is we want to be able to interpret these signals as a signature. To be able to say, I want to be able to classify, I'm looking at this signature now. Which satellite is it actually coming from? And so we're going to now assign different signatures to the satellites that they will then transmit to us using electromagnetic waves. So let's say I have some, how do I draw a satellite? I don't know, some satellite like this. And it has, let's say, it wants to transmit a signature to us. So let's call this satellite A. And it's going to choose to transmit its signature. We're going to represent this as a vector. So signature of satellite A is going to be a vector. And let's say that it chooses 1, 1, minus 1, minus 1, 1. Okay? And it's going to transmit this to us as a signal. And so for this, I want to introduce this idea of representing a vector as a signal. So I'm going to draw this vector in a particular way. 0, 1, 2, 3, 4. So there are 5 elements here. I drew 5 points here. The first thing is a 1. 1, 1, minus 1, minus 1, 1. all I did was I drew a picture of this vector, right? Everyone see that? Okay. And I'm drawing this picture out because it's going to represent how the satellite is actually going to send this signature to us. Basically, the satellite is going to send information to you by basically sending out a signal of plus ones and minus ones, or zeros and ones, depending on how you want to talk about it. And it's going to send a particular signal if it wants to send a 0. It's going to send a different signal if it wants to send a particular signal if it wants to send a 1, another signal if it wants to send a minus 1, right? And this is typically a voltage, for example, or an amplitude of an electromagnetic wave. But we're not going to get too much into the physics of how this is implemented. For that, take 123 if you're much more interested in this. Let's say at every time step, every second, which this actually operates much more faster than something every second, but it sends you a 1 or a minus 1, right? And then you say, I know that the signature is of length 5. I wait for 5 time steps, and then I collect my vector, and then I see what signature this is. Okay? Does everyone understand how this signature is going to be transmitted? It's going to be transmitted as this signal. And the reason I'm drawing it this way is because at the 0th time step, the first element of the vector is sent. Then at the first time step, the second element of the vector is sent, so on and so forth. Okay? So now let's say there was a second satellite B, and SB had some signature, let's say 1, minus 1, 1, minus 1, minus 1. And this also you could draw. And you could write this out as 1, minus 1, 1, minus 1, minus 1. 0, 1, 2, 3, 4, 1, 1, minus 1, minus 1, minus 1. Okay? So these signatures, as you will see on your homework as well as in the lab in the implementation of this, are what are called gold codes. And every satellite is assigned a pattern of plus and minus ones, which is their signature. And they basically keep transmitting this signature out. That way, whenever I receive that signature, I know that I've received a signal from this particular satellite. And every satellite has a different signature. Of course, they're not these super short sequences of length 5. Gold codes are much longer. In the lab, you will be using gold codes of length 1024. 1024. And we now want to go to understanding how we can disambiguate these two satellites from these signatures. Yes, question? Great question. The question was, is this similar to or analogous to Morse code? And the answer is, in many ways, yes, it is very similar. It is very similar. Morse code basically assigns for every letter, for example, of the English alphabet, a symbol of dots and dashes, right? Here you can think of the dots and dashes as plus and minus ones, and every satellite is going to be assigned this kind of signature. And we want to now be able to figure out from these signatures a lot of different properties. So in that sense, it's very, very similar. And if you want to understand more about how these kinds of codes are developed, a class like information theory, which is 229B, would be super interesting to take. It'll talk a lot more about this. There and then there. Great question. How do you know when time 0 starts? This is exactly the problem about clock synchronization. For now, we're going to pretend that we know exactly how the times are synchronized. Upper division classes, probably maybe 149 talks about this. I'm not entirely sure, but that might be a class that'll explore that a little bit more. Yes, question over here. Same question. Okay. Other questions? Yes. Does this hypercubes? So when I think about a hypercube, I think about the cube that has vertices that are at that is of volume 1 in hyperspace. But maybe you mean something different.
Instead of showing 0, we're showing -1 means no signal.
Maybe let's take that off of outside of class, because I'm not sure that it's relevant to the entire classroom. But yeah, let's talk about that right after class. Other questions? Okay, great. So we have these two signatures. Now let me think about what I receive. I receive this vector r. My received vector r, what would I want my received vector to be? In an ideal perfect world, I would receive 1, 1, -1, -1, 1. Right? I receive this vector. My cell phone antenna receives this vector. The satellite is transmitting this. And what would I conclude if I received this vector? Satellite A was transmitting, right? That would be the perfect ideal world. But in reality, probably what is the received vector you would get? It would be like 0.9, 1.1, -1.2, 0, 1. I receive something like this. What do I receive? I receive, in fact, S plus some noise vector. Received, this is sent, and this is noise. Now when you receive this, how do you know what was actually sent? Right? This is the problem that we want to now be able to solve. How do you classify in the presence of noise? So does anyone have any ideas on how we might go about doing this? It's a design problem, right? We want to think of ideas. Yes? Great idea, right? Take another reading, right? Take another reading and average it out. Ask the satellite to transmit again. Excellent idea. And in 2 lectures, we're going to be talking about a variant of this idea soon enough. Yes, at the back. Are there filters that we could use to somehow reduce the noise? Yes, usually these signal processing systems will have filtering that will reduce the noise, but often even despite that, noise will creep into your system that we still need to deal with. Great questions, or great ideas rather. I'm kind of rigging it. I just spent a half hour talking about one idea. If that wasn't going to be used in the answer. Yeah.
It's not that idea, but like maybe figure out which code is closest to.
Yep, great. The idea was figure out which vector it is closest to, right? And this is a very, very good idea, which I in fact want to build upon. So I have my received vector r. Find which signature r is closest to. And this is getting to now a core thing that you will often have to do in any machine learning problem, which is you have some sense here. You want to say that I want to figure out which satellite actually transmitted this received vector. And I want to figure out now which signal is r close to. But this notion of close is something that I now have to define, right? I'm designing the system. I'm the engineer, so I get to decide what that metric is. I get to decide on an error metric. So I choose my error metric, and I say, let me define my error E to be basically my received signal minus the satellite signal. So I will have basically an error metric for every single satellite signal, right? So the error with respect to satellite A is EA. Error with respect to satellite B is EB, and so on, right? Question at the back? Okay. What we want is to find that satellite such that the error is minimized. And when we think about vectors, what is the metric that we use to figure out how big a vector is? It's the magnitude of the vector, right? So we're going to look basically at the magnitude, or the magnitude squared, of this error vector E that we have just defined. I'm dropping the subscript A or B. We'll just do this regardless because it doesn't matter which one we're doing it for. So I want to figure out which satellite actually minimizes this error vector, right? The received vector is given to me. Do I have any choice over R? No, right? This is given, it's there, I have nothing I can do about it. Now I want to figure out which S is such that this is as small as it can be. So I can write this problem as minimize, M-I-Z-E. Minimize the norm squared of E over all satellites. So here, now you have done two things that are commonly done in developing any machine learning algorithm. First, you chose an error metric. Now what you're doing is you're writing an optimization problem over that error metric. You're saying, I want to somehow find that satellite that minimizes this error metric. These are subtle things that I'm trying to spend time on to emphasize, because how to make these choices is what we are hoping that you can take away from this class. Everyone with me here? Okay. So now let us explore this quantity. Okay? How can I write this? I just found out that this I can write as E, inner product with E, right? This is the same as E transpose times E, right? But what is E? E is just R minus S transpose times R minus S. Everyone with me so far? Okay. What is the next step? I want to take this transpose inside. I can write this as R transpose minus S transpose times R minus S. Further writing this as now R transpose R, just using distribution. Then I have minus S transpose R and minus R transpose S. Right? Does everyone see that these are the four terms that you get out? I'll pause for a minute so people can catch up. Make sure that you've understood the manipulations that I've done so far. Okay. Any questions up till here? What is R transpose R? Can I write this as something that I know? It's the norm of R, right? Squared. S transpose S is the norm of S squared. And what is this? This we just defined today, right? We can write this in the notation we defined. S transpose R is equal to R transpose S. This is minus 2 times the inner product between R and S. Okay? So now, when I'm looking at minimizing my error, what am I actually looking at minimizing? I'm looking at minimizing this expression, right? Can I change the norm of R? Nope. It is what it is, right? This is fixed. Can't change that. Can I change the norm of S? What are the choices that I'm looking over? I have many different satellites, right? So potentially, hypothetically, I could have different norms for the signatures of the satellites. Turns out that you can choose to design these, right? You have the control of designing these signatures. No one's giving you these signatures. The engineer gets to design these signatures. So you can pick these signatures, and that's how these gold codes are designed, to all have the same norm. They're all vectors that are plus or minus 1. So the norm of these vectors, as we chose here, are always the same. They're always just the length of the vector, right? So here you see that norm SA is equal to norm SB, and this is fixed. So then here, this is also fixed, which then says that basically the variable that you have to play with is this inner product between the received vector and all of your different satellites. So now when I write minimize, can I rewrite this optimization problem in terms of what I've seen? By choosing S, by choosing the different S's, can I change this expression? Nope. Can I change this expression? Can I change this? So can I replace this by this term minus 2 inner product of R and S? This is the same as minimizing minus 2 inner product RS. So instead of minimizing a negative quantity, what's an easier way of writing this? Maximizing a positive quantity. And if I maximize some number x, is it the same as maximizing 2x? Does this 2 matter? Not really. So I can rewrite this as maximize RS. So I'm going to write one more thing and I'm going to take questions. So if I wanted to now use this insight to design a classification algorithm, what am I going to do? I'm going to say for all satellites SI, compute inner product of R and SI. Return I, that index I, of satellite that maximizes this inner product. So what am I going to do? I have my stack of satellite signatures, right? Every satellite has told me in advance what their secret signature is. I take what I received, and I take this inner product. Right? So if I have 24 satellites, how many inner products do I compute? 24. I look at all of them, and I say, which inner product is the maximum? Whichever one is the maximum, that is the satellite that minimizes our chosen error metric, right? We wanted to find that satellite that is closest to the vector that we received. So this is a lot of stuff that just happened here, and it's subtle. So I'm going to pause for a minute, think of a question that you have about this topic, and write it down, and then ask me questions. So just take a 30-second pause to think about what questions you have. Feel free to talk to people. Okay, how many people are perfectly comfortable with all of this? Anyone has any questions? Yes? Why did I start with minimizing this? Great question. So this is exactly excellent question. So what we're saying is that we want to figure out, which satellite is transmitting. How do we go from there to here, right? This is where our modeling and our choice of error metric, this is our choice as the engineer. So we're saying, well, we received this vector, and we have these two choices of satellites that we're transmitting, right? Let's look at R minus SA and R minus SB. And they give us these two error vectors, right? And so let's say I had 24 satellites. I would have a list of 24 vectors. I want to find that satellite that is closest as a vector to my received vector. So if I was to draw this picture, let's say my received vector was here. And let's say satellite A was here, and satellite B had the signature here, right? So R minus SA would basically give me this vector, and I have R minus SB. It would be pointing in this direction. R minus SB is that vector, right? So these are my EA and EB vectors. And I want to say, let me figure out now which of SA and SB is closer by looking at the lengths of these EA and EB vectors. And that's why I'm looking at now minimizing this. And this is not, it's important, your question is excellent because we are making this choice, right, as the engineers, to say this is the metric that we want to minimize. We could say, let us count the number of, 0.35s in the vector, or let's count the number of ones in the vector. You can make up whatever metric you want and say, let's minimize that metric. And that may or may not be a good metric. We are choosing this metric because we believe it's a good metric, and turns out it also works. So it is a non-obvious step. Yes, question? How do we know that the answer to this optimization is unique when we do this? How do we know that there's only one maximum? Another excellent question, right? What if you have a pretty similar measure for two satellites? How do you know that there's only one maximum? Excellent question. This again is in the design of the gold codes. And the way you design your gold codes is so that each gold code is basically orthogonal to all other gold codes. So each signature has a very small inner product with every other signature. And this is exactly what you're going to explore more in the homework as well as in the lab. So you will see that by carefully choosing this, you can make sure that you will not have two maximums. And you rely on your power as an engineer to design in doing that. Yes?
Is the quantity negative 2 times the inner product of RS bounded by something? So I'm assuming it can't be smaller than like the magnitude of RS.
So here, this, right? So you're saying that, yes, this is going to be upper bounded by the product of the magnitudes, by the Cauchy-Schwarz inequality that we just talked about. Yep. The question was, is this quantity fundamentally bounded? Other questions? Yes? Great question. The question was, why do we say that the norm of S is fixed? And we say that the norm of S is fixed because, again, we're making that as a design choice. We're saying that we are going to be transmitting gold codes, which are basically plus and minus ones, or zeros and ones. And as a result, we can choose to make these fixed. We're doing this so that we can, again, use this inner product as our proxy for figuring out what is the best transmission. So just to summarize what we talked about here, right? We went basically from this idea of a classification problem to defining a model and an error metric, and finally coming up with an algorithm. You've solved design problem 1 of module 3. Design problem 2 will come next lecture.